Hello and welcome to the webinar. My name is Josh McDaniel and I work with the Wildland Fire Lessons Learned Center. And in a few moments we'll start the webinar, but first I want to make a few quick notes and announcements. First I want to point out that the webinar is co-sponsored by 3 different organizations: the Wildland Fire Lessons Learned Center, the International Association of Wildland Fire, and the Joint Fire Science Program. Oh, I see that the Northwest Fire Science Consortium is up there as well. That was from a previous webinar, but they are definitely friends of the group as well. I want to point out the next upcoming webinar is going to be by Mark Wallace and Tom Patterson. Mark Wallace is the Wildland Fire Specialist for Esri, and Tom Patterson is the Wildland Fire Specialist for Esri, and Mark Wallace is the GIS Unit Manager for the Queensland Fire and Rescue out of Brisbane, Australia. And they're going to be giving an example of using mobile technology on an emergency incident, not a fire incident, but in this case it was a flooding incident in and around Brisbane. And then Tom is going to be talking about how the same system they use in Australia could be applied to wildland fire. So I encourage you to tune in for that. That's going to be on May 28th, and we've moved that to a different time, to 3 p.m. Mountain, later on in the afternoon, to allow some of the friends from Australia to tune in very, very early in the morning if they're available. Okay, I'll introduce the speaker in a second, but first I just want to let you know how a few things work with the webinar. If you have a question, and we encourage questions and encourage you to get questions early, you can type them into your questions box, and for some folks it might say chat, but either way, questions or chat, type it in and we'll get it. At the end of the presentation we'll have a Q&A session and we'll read through those questions and have Matt Reeves, the presenter, respond to them. But the sooner you get question in, the further up the queue you are, the better chance we have of getting to it. So get those questions in. Next, I want to point out that the webinar is being recorded, and we'll post that the recording for that webinar on Advances in Fire Practice. And I've put a screenshot of the Advances in Fire Practice webpage down below, along with a link there beside it, which you can also register for that upcoming webinar. And see any of the upcoming webinars, see webinar archives, any of the articles, that sort of thing. And that's a Wildland Fire Lessons Learned Center website. So, on to today. The presenter today is Matt Reeves. Matt Reeves is a postdoc research ecologist with Rocky Mountain Research Station in Missoula, Montana. He received his BS in range management and MS in environmental resources and his PhD in remote sensing and ecological modeling of non-forest and agricultural environments. Dr. Reeves specializes in geospatial applications for characterizing status and trends of non-forest biomes and was the fuels team's leader for the Land Fire project. And with that, I will hand the screen over to Matt and allow him to take over. Welcome, Matt.
Well, thank you, Josh, for your introduction, and thanks to 27 attendees that took the time to hear me today. Start the presentation now. As Josh said, we're looking at quantifying biomass and fuels for non-forest lands of the Coterminous U.S. I should mention that this research was funded by the Western Wildland Environmental Threat Assessment Center, and I want to give them thanks for doing so. We're going to first talk about, in brief terms, what this presentation will look like. First, we'll discuss the scope of the problem and kind of try and figure out why it is we are doing the work and provide a rationale for the project. In other words, why did we become interested in doing this work and why we think it's important. Then we'll describe the process, and I'll walk you through the processes we use for estimating biomass across the landscape and how that translates to fuel beds in non-forest environments. We'll look at the spatial domain for applications and some of the implications of that domain and what it may mean for managers. And finally, we'll discuss results in terms of biomass and fuels from 2000 to 2012 with some selected regional examples to drive the point home of how this system works and what the results of it look like. First, I want to get a couple of points across, and that is planning and decision support, as you know, require a good deal of information and fuel data. Fuel data are useful for a lot of reasons, but two basic uses of fuels data exist currently, and those are strategic and tactical uses. For strategic uses, we're looking at questions such as, where do we think we may have problems in the near future, and where would we allocate our resources and time to alleviate those problems? Second would be the tactical situation, where we are interested in describing fire behavior on an incident. Now, the Land Fire Surface Fire Behavior Fuel Model Suite, and for those of you that do not know about the Land Fire project, I apologize, we don't go into that project much. Just suffice to say that it's a national project that was designed to provide fuel data and vegetation information at 30 meters for the country. Now, they originally mapped these surface fire behavior fuel models, both the Anderson Suite and the Scottenberg 2005 set of fuel models, but they represent the landscape circa 2001. But they subsequently be updated to represent 2008 plus or minus, but only for disturbed areas. So they're only looking at updating in disturbed areas. So that leaves a large part of the landscape probably unaccounted for. So this is what this kind of describes, this line graph kind of describes the situation we're in. So fire, in this case, this fictitious site in 2000 was operating at some level of production, and then it was skimmed off by the fire, and the productivity dropped significantly as a result. And this fire, this type of event, this type of perturbation to the system is accounted for in the land fire system. Okay, they look at these disturbances and then map what happens. But what we are after, though, is the interannual productivity, which is not currently accounted for. So how do fuels vary interannually? Further, we are interested in the fuels part, obviously, of the fire triangle. And as you can imagine, as this line depicts, this could be variation in fire number, fire size, fire starts. It varies year to year. And that's in response to fuels, weather, and topography. We're, of course, focusing on the fuels part of that equation. So in terms of our area of interest and where we're applying this information, we're applying it to the Coterminous U.S., but only in rangelands, so non-forest lands of the United States equal to plus or minus 660 million acres, or 267 million hectares, encompassing deserts, shrublands, grasslands, and other selected biomes. But this is the spatial extent where we're applying these models and information. To further illustrate the situation we're in, you have this desert landscape on the top left-hand corner that is showing us, don't need a McAfee stand, that is showing us the Scottenberg and the Anderson selected fuel model, for example, for an area. You might even consider this non-burnable in this desert environment. Well, and that has associated relatively low fire behavior. If we look at, though, a year where there is abundant herbaceous growth due to precipitation or some other event, then that really increases fuel bed continuity and fuel loads. And therefore, we need to have a system to update that expected fire behavior in response to that. To further illustrate, we've got two desert landscapes shown here, a Sonoran desert landscape on the left and Mojave on the right, where exotic perennials, native annuals, and exotic annuals all come together in years of sufficient moisture to really create very different fuel conditions, basically increasing fuel load and fuel bed continuity. So you can imagine these landscapes look markedly different in a good rainfall year. Now, this is very important to understand, which is the variability of our non-forest systems. What I have here is the variability of systems in terms of interannual variation in productivity. Cooler tones represent areas with high interannual variability. So you can see areas of the west and southwestern U.S. exhibit very high interannual variability. The two most variable systems we have today, by estimated from satellite, are the shortgrass prairie types and the lower Sonoran in southwestern Arizona. So those are our two most variable systems at about 25% per year. So that means on average they're varying 25% per year over a 12-year time span. Well, if we look at an individual year and see what this looks like, in 2005 we compared each year of the time between 2000 and 2012 to its respective 12-year mean, or 10-year mean in this case. And what we see is that in 2005, the Southwest experienced a huge flush of growth, represented by these pictures here in the bottom of the slide. And that was, in some cases, 150 to 200% increase in fuels and overall production. What I'm going to do next is toggle back and forth between the fires that started in the area and these areas that are very dark blue. You'll notice that the fires tend to occur in that year where the fuels were very abundant. So I'm just sort of toggling back and forth to give you an idea of the relationship between fire outbreak. These are large fires, mind you, not the small ones. Large fire outbreak and the prevalence of fuels in the southwestern United States. Okay, so the scope of the problem, in summary, is that field data are needed for strategic and tactical purposes. There are other purposes as well, but we focused on these here. Second, the interannual variability in biomass is very high in rangelands, especially when you compare it to forested situations. I mean, forests don't vary 150 to 200% per year. That just doesn't happen in forests, but certainly so in non-forest environments. We're talking about large landscapes in a situation where field data are very scarce. So our proposed solution to this problem of updating fuels is to get something that's wide scale, that covers a large area at relatively low cost, and that enables us to monitor. And that's really the forte of remote sensing. So already we're kind of focusing in on a remote sensing approach to this problem. Now we should also be able to monitor with this, and we should incorporate local knowledge where appropriate. In other words, include managers' opinions and knowledge in the matter if we can. We must also operate at an annual or subannual timescale. A subannual timescale is possible, but not currently operational. We're just looking at an annual time step. And it must be malleable. In other words, as we learn things and understand landscapes more completely, we should change or update them, and that should become very easy. And finally, we need to provide widely used and well-known fuel metrics from this process. So we're looking at something that's low cost, that's reasonably useful, that's relatively timely. And for that, I've captured this program in this basic flow chart here. And of course, the first is it's a biomass and fuel monitor using remote sensing, that's RS, and biophysical modeling. All right. Well, in order to develop this biomass model, how are we going to estimate biomass across the landscape? And in order to develop a suitable model, we have to have a way of understanding what conditions are like across a lot of landscapes. And one way to do that, perhaps not the best, but one way to do that is to use the Soil Survey Geographic Database, or SURGO, which is basically just the soil surveys in digital form of the United States. With the SURGO data set comes annual production in non-forest environments, where they actually went out and clipped and weighed and assigned 3 different values to each soil series: drought, normal, and a favorable condition. So let's look at 3 of these soil types and how they relate. The production relates to NDVI. NDVI is on the Y, and that's normalized difference vegetation index. Suffice to say that it has been used widely in the remote sensing community to describe biomass and productivity both. On the X is rangeland production pounds per acre. So we see this first series is the binge. It is a sagebrush steppe. It has its own unique curve, and the 3 points in this case represent high, medium, and low, or drought, normal, and high productivity. Likewise, with the shortgrass prairie, a little more productive in the Boot Hill series, and finally the glacial, which is a tallgrass prairie example. So these are all relations of those soil series to NDVI. Now, there are problems using the SURGO data set, and seam lines is just one of those. But I wanted to point that out. We fully acknowledge the difficulties in using the soil series data as a proxy for field data, but we simply don't have rangeland production spanning wide areas of the United States. So if we have annual production from SURGO, and we combine that with vegetation types, in other words, what kind of vegetation is present in the biophysical setting, in other words, the site conditions, with precipitation, and with that we're looking at the high precipitation, the average precipitation, and the lowest precipitation at any given pixel or any given site over a 12-year period, 2000 to 2012. And we have the concomitant with that is the maximum NDVI. Okay, so we combine all these things together in order to be able to predict the annual production. Well, let's look at NDVI a bit more carefully. I wanted to point out a few things. First, there's 26 plus or minus periods in a year, depending on how you slice it. It's a biweekly product. It can be a little noisy, as these dots on the chart suggest, but it's 250 meter spatial resolution. That's roughly 6.25 hectares. So if we look at the NDVI in a given year, we apply a smoothing function to this so that we take out some of these sort of wild jumps in the NDVI. And our assumption then is that the maximum NDVI is equal to the maximum biomass, or can sufficiently describe the productivity. And I think, I hope that I can convince you that that's definitely the case with respect to our work. So we put all this stuff together, and we come up with a biomass production model that looks something like this. And of course, it combines all these components: precipitation, the maximum NDVI, and then these unique site identifiers, or coefficients. So for each site we identify using existing vegetation and site parameters, those different sites will have unique relations to NDVI, and so we want to capture that. And of course, we also have their associated interactions as well. On the X here is our Y, which is our target, is our explained Sergo production. And then our predicted Y is the result of our cross-validation and applying the model to our known Sergo points. And so we can predict what we have found with reasonably good certainty. But we need to then apply this on the ground. Well, we know that each site has different coefficients, as I alluded to. So as you can imagine, a sagebrush steppe vegetation that's depicted here, infested with cheatgrass, will have different values than, for example, a tallgrass prairie. Unique relationships with NDVI and precipitation. And we've captured those in this model. So we've talked about developing the production model. We used MODIS, Moderate Resolution Imaging Spectroradiometer, satellite data, which is the NDVI, plus our biomass, plus our landscape attributes. And then the next step would be to quantify our annual production, okay, from 2000 to 2012. This is current growth, not increments. So when they sampled this, when they went out in Clifton Way, they didn't increment bore shrubs, for example, to determine how shrubs were expanding. They just looked at the low-hanging fruit, which is usually the herbaceous and some of the leaves, the new leaves of the shrubs. So we're really talking about fine fuels here. But in order to get a full field picture, we also need to understand what the holdover looks like, and I'm calling the standing dead the holdover. We'll talk about that more. And finally, after we quantify, we need to compare what we're currently seeing to our reference conditions to determine how far away from our reference or our average are we today or this year. So by holdover, I'm talking about the decadent and dead from the previous year. So we need to account for not only annual production, but also the holdover. How do we do that? It's pretty simple. We have a suite of unique functions. One of them is shown here for a sagebrush steppe and cheatgrass-infested sagebrush steppe, I believe, in southern Idaho. And we've got a holdover in %. And then on the X is years since production. Okay, so there's sort of a decay function that represents how this dead material of the grasses will decay and not become available in the fuel bed through time. So let's look at some math here briefly, see how this turns out. For our cheatgrass-infested area, in terms of production, let's say we have from 2012 to 2013, we have values ranging from 1,100 to 700. So 2013 is a dry year. Let's say they're on the low end of the spectrum there. Okay, so the current year's production is 700 pounds per acre. In this case, of fine fuel, of annual production. But we have to include in that, for our fuel bed, also the standing dead. So if we use that curve that's up above, and we apply that to the successive years of biomass information, and we simply add the previous 3 years' worth of information together with the present year to come up with an estimate of 1,225 pounds per acre, which includes mostly herbs and some shrub shrub leaf. So it's total ecosystem production for a given site. Okay, I've shown you how we determine what biomass is probably doing at a given site for the present year, but we need to translate that into what that looks like for fuel. So we can tell when and where changes have occurred. We pretty well know that. And I'm using finger air quotes and saying we know that, but the real trick is to determine how to change the fuel data. So what do we do with that information in terms of fuel? And this change process is governed by what we call our fuel transition matrix. And this matrix is responsible for informing the program as to how to transition between various fuel beds or fuel types in response to biomass. So at this point, we've quantified our fuel conditions. Now we need to consult our lookup table. And this has 23 ecological provinces. So LUTs is equal to a lookup table here. And we're going to update the fuel model assignment, surface fire behavior fuel model. But at this stage, if you wish, if you have a program that can, a surface or a fire behavior processor that can use just straight up fuel information, fine. You can use the fuel load data itself to make other fuel classes. For example, you could implement that within a fuel characteristic classification system to determine unique fuel beds. Well, let's take a look at the approach we used here, which is the fuel transition matrix for each ecological province. We have 23 unique ecological provinces, and for each one of these provinces, we have a unique lookup table that can govern how the program will change between various fuel models. Well, let's take a look at that fuel matrix bit, open the hood, and make it unblack box. So for one area here that I picked, we're only looking at fuel models that represent non-forest environments. Remember, that's our target. We've got the name over on the left-hand side, GR1, which is a grass one, GR2, which is a grass 2, etc. Let's take a look at how this translates to fuel model updates. Well, the GR2, in this case, second line down, represents a fine fuel, or suggests a fine fuel of roughly 2,200 pounds per acre. Well, let's just say that our live herb, which it also suggests at 2,000 pounds per acre, has been increased by, say, 50%, so 1.5 times 1.5. That gives us an estimate of roughly 3,000 pounds per acre of live herb, or roughly, say, 3,400 pounds per acre of fine fuel. Well, now we're kind of stuck because we're a GR2 and we're at 2,200 pounds per acre target, but in reality, we're much greater than that. And so when we come up against a situation where we've got, say, double that, so now we've gone from 2,000 pounds per acre to 4,000 pounds per acre in a very wet year, we need to really consider updating from a GR2 to, for example, a GR4 or a 104 based on the fuel load. Okay, and based on the fact that we have 23 of these different lookup tables for every, or rather for the United States. So that's how we transition between different fuel models, is looking at what the current fuel model is, comparing that to present conditions, and updating according to these transition tables. Let's look at some results. What we have here is the fine fuel from 2002, and you can see that 2002 was a very dry year. It was regionally dry, and we have fine fuel in pounds per acre. This is an actual result from the program. Compare that with 2010. It was regionally wet, especially up in our neck of the woods, up in Montana, the northern Great Plains. We really had a flush from tremendous rainfall, deep snowpack. We had a lot of herbaceous material on the ground. Well, let's look at the change in fine fuel then, according to some other processes. Well, in this model, we change or compare our fine fuel estimates by year to the load suggested by the Land Fire Surface Fire Behavior Fuel Model, or FBFM. Now, I'm not picking on the Land Fire project in the least, just to say that it was the only one available at this sort of regional level that I could compare my product against, or our product against. And I know it's sort of a bastardization to compare fuel loads to a surface fire behavior fuel model. I get that. And this information is not necessarily used in how we transition the fuel data. What I wanted to show you, though, was how our estimate of fuel compares with the suggested fuel bed properties of the land fire system. Okay, and what you can see then, and this is shown in percent. So if we're red, that means that our estimate says actually our fuel bed and our fine fuels suggest that we're about 90% less than what the surface fire behavior fuel model currently represents in its stylized fuel model. All right, and if we look at 2010, that changes. Actually, in the upper Great Plains, the northern Great Plains, southeastern Montana, you can really see things greened up hard. And what that tells us is that in those instances, compared to the land fire, surface fire behavior fuel models, our data suggests that perhaps we're much more abundant than the fuel models are currently letting, suggesting that we could see increased fire behavior relative to what is being presently shown. And I just wanted to show this information just to give you an idea of how the types of information we're providing compares to a product that's out there, and how it compares to its stylized fuel bed properties, and that being fine fuel. Okay, well, another product of this system enables us to look at the changes in fine fuels of every year of analysis versus the 12-year average. So how was 2012 relative to the 12-year average? How was 2010 to the 12-year average? And it gives you an idea very quickly of how we can track regionally these favorable or unfavorable growth conditions. So let's take a look at 02. 02 is regionally dry, and in fact nationally dry if you look at this depiction. And we're suggesting we're at least 25% lower in these sort of peach tones. Okay, don't criticize my color scheme because I'm terrible with these, but I just wanted to point this out that it's the peach color here. So we're in the minus 25 to plus or minus 50% less category. So we've really swung down in 2002 in terms of fine fuel and productivity for the western United States. But if we look at 2010, just the opposite is true, and we really greened up. And so in 2010, we swung the other way. We're 25 to 50% increase because we were regionally wet throughout much of the western U.S., but especially in the northern Great Plains. Now, of course, there's a lot more detail in these maps than you can make out in these presentations. I'll share these data with anyone who's interested in a raster format. Okay, I want to also clarify one thing, and that's we can obviously go both ways. I think I've demonstrated that. We can either go from, say, for example, a grass shrub 2, a GS2, to a GR1, or perhaps even a non-burnable and extreme scenarios for the year. But we can also go from, a GS2 back down to a GS1. We can go the other way. So we can go from hot to cold or cold to hot, either way. And the product is sensitive to grazing, it's sensitive to treatments, precipitation. In other words, we don't know exactly what is causing the change. We just are observing the change via our biomass model. Okay, we just know what happens. We don't know why it happens. Okay, let's zoom in a little bit and increase the resolution some. 2002 was a dry year in Montana. Okay, so you see an awful lot of red, and this is biomass. It's in pounds per acre. So we're looking at a dry year compared with 2010. It was a very wet year. We use this exact kind of information to guide our fuel model selection. So let's take a look at what that means. In 2002, again, this was dry, our surface fire behavior fuel model. It's going to be very hard, unfortunately, for you to determine these changes on the PowerPoint. But look in the lower right-hand part of the screen, corresponding to the areas that really greened up. Okay, you can subtly see some changes. I'm going to show you what that means in acreages in just a second. Okay, so I'm toggling back and forth between a dry and a wet year to give you the idea that we're able to capture these large variations. Let's look at the results. And again, this is for Montana. So on the Y, we have area. Doesn't matter the units for this talk. It's the distribution we're interested in. And we have our distribution of fine fuel in pounds per acre. So this represents non-forest landscapes in Montana that we evaluated. And in 2002, you can see the mean, the peak of the curve, is definitely bunched towards around 1,000 pounds per acre, whereas the mean in 2010 was up around 1,800 pounds per acre. So you can see how the biomass distribution really changed, and we captured that spatially and temporally. And so what that means in terms of fuel model changes, let's have a look and see what that did to our fuel models across the landscape. So what I have here is a table that shows us fuel model, and then the change in that fuel model from 2002 versus 2010, in area in acres. So how did things change? Well, we lost about 3 million acres plus or minus of GR1. Very slow-moving, low length fire conditions. We transitioned a lot of that to GR2, the 102. So we gained 2.6 million acres of GR2. The 103 we lost, and in the 104, the GR4, we gained almost 250,000 acres. All right. Losers were GS1, represented by the 121. We lost 262,000. And a lot of that got shoved into the 122 or the GS2. Basically, we ramped up. What it's telling is we ramped up big time from 2002 to 2010 in terms of fuel bed conditions and the associated fire behavior metrics that can be derived from these fuels. So to capture this, we have updated the fire behavior fuel model data products for Coterminous United States. So that's 660 million acres, those non-forest areas. We've got maps updating each one of those for every year from 2000 to 2012. Now, we were able to sort of shrink wrap our 250-meter biomass process, our biomass estimator, down to 30 meters using some filtering and other types of GIS techniques. So we've got a 30-meter product from 2000 to 2012 depicting updates in surface fire behavior fuel models. There's also associated with these not only the fire behavior fuel models, but remember, if you're of the ilk that's just interested in the actual fuel quantity, that is available as well. And hopefully this becomes an operational process. Of course, we all hope that, but I think that this one has the opportunity to do that. And in fact, I've been in contact with some of the land fire leadership. We have discussed this possibility, and I have high hopes for it. I think it could benefit that process quite a bit. It really wouldn't cost a whole lot of money. Once we've got a monitor in place, what's needed is to feed it data. You need a data warehouse. You need a computer to crunch it. You need a dissemination host. That'd be another computer. And an integration process with, say, for example, the land fire system. Once you have those in place, you're pretty well ready to go. Let's talk about accuracy. And I'll say that for this type of situation where we're predicting and updating surface fire behavior fuel models, there's really no such thing. And we could estimate the accuracy of our fine fuel, certainly, if someone had widespread data that they could share that would show us how fine fuels have changed year to year. We could compare that to our temporal profiles and look and kind of compare. But in reality, with the surface fire behavior fuel models, that's kind of hard to do. There's no such thing. But we can look at an efficacy assessment. In other words, how well do these fuel model updates allow the decision support systems to give us better answers? Okay, so that's really what I'm interested in, is how well do these data work for their stated purpose? So to do that, I guess there's a lot of different ways to skin the cat, but we're looking at 5 to 10 study sites where a lot is known. We know something about fire perimeters, fire behavior accounts. In other words, what happened when did the fire make a run, when did it shut down? And we want reasonably good weather, meaning what was the fire weather like when the fire made that run? And of course, getting this type of information is difficult. Getting clean data is always difficult. That is our goal. What we will do with this information is match new fire behavior projections with the perimeters that were shown to us for each site. So hopefully we get a better match in terms of fire spread and overall size using these fire behavior fuel model updates. With that, I've ended a little early because I was hoping we could entertain some questions at this time. But I want to thank you all again for listening, and you can reach me at any time at my email here or my phone number. It's my cell, so I'll be pretty well available just about any time. Again, thank you for listening, and I'll entertain any questions.
Okay, thanks, Matt. And that was a very comprehensive coverage in a very short amount of time. It's very appreciated. So anybody else out there, if you have some questions, get them in. There's no questions at this time, so well, I guess while we're waiting for a couple to come in, Matt, maybe you could talk about what you're going to be working on next with this. Is this something that's going to be irregularly? Is this project going to be?
Yeah, the project, as I alluded to, I'm trying to work out the details with land fire leadership and see if they have any use for these types of information, which I think they probably do. So we've been discussing that for a while. So I'm going to be looking at ways of integrating this into that system. It's unknown if that occurs, but it's our desire. And the second thing I'm going to look at is using the same suite of predictive information, the same type of modeling approach. What we've discovered is, in terms of non-forest fuels, we can actually, I think, come pretty close to a forecast in terms of what we're going to see. Now, obviously, we're not promising anything with forecasts because that's tricky business. But I can tell you what we've seen so far is that we can explain probably around 75% of the variability in observed biomass probably a month and a half in advance, depending on the system we're interested in, because of the climate that we're seeing that year, because of the the meteorology that's driving that system. So in other words, if we get X amount of rainfall, X amount of thermal units by April 4th, we know that in the peak of green that we're probably going to be seeing, say, 1,300 pounds per acre, which translates to XYZ field bed conditions. So that's another area of further research.
Okay. I have a question that just came in from David Weiss, and he says the focus of the presentation seemed to be grasslands primarily. Will the approach work with woody shrub vegetation given the differences between grasses and woody plants?
Yeah, if we're talking about pure shrub systems, say for chaparral, I think there is a difficulty because of the way the Surgo data were sampled. In other words, they just stripped the leaves in a lot of cases, which some of you may or may not know how this was done, but they would take the new leaves and then dry them and weigh them for individual types, but it was really aimed at forage in a lot of cases. So in the case of chaparral, they were, I think, probably undersampled. And having said that, I think there probably are ways of tweaking it. It works better when you have a mix of shrubs and grasses or of just herbs than a pure shrubland, for example. So if you're talking about an Artemisia tridentata, a big sagebrush stand with almost no herbaceous cover underneath, that's going to be a pretty tricky scenario, partly because the spectral response of shrubs doesn't vary as much as it does for herbs, so it'll kind of look a little blah from 700 kilometers in space.
Okay. Ron McQueen wants to know if these biomass outlooks are available on the web.
No, but they're available from my computer. I haven't translated this to the web yet.
Okay. Yeah, so if somebody's wanting to get, say, a zoom-in look at their state or their local area, they should just contact you.
Absolutely. I'm the primary point of contact until we get some coverage on the internet. It is my intent to wrap up, when we wrap up this project, to make everything available, perhaps including the computer algorithms used for the biomass.
Okay. Well, Matt, that's all the questions we have right now. So well, I want to thank you. That was a very interesting presentation, and we look forward to more of this to come.
Hey, I want to thank all of you for listening, and have a great day.
All right, thanks, Matt. And if the webinar is being recorded, I'll have the recording uploaded in probably about an hour on the Advanced Fire Practice. You can pass this on to anybody you think might be interested. All right, well, thanks, everybody.
Have a good day.